Hello, everyone, and welcome to ARMA Hydraulic Fraction Community online seminar. It's the first seminar in 2022, so I hope you had a great Christmas and New Year's break, and you start your new year strongly. First of all, I would like to take this opportunity and thank the organizing committee for inviting me to speak, and thanks for this online seminar series. So I'm a big fan and a huge supporter of this online seminar series, because I think it's a way to essentially limit the borders and the boundaries, so that we can all meet and use technology to meet despite the turbulent times. So first of all, I'd like to start with my favorite quote from Benjamin Franklin, that an investment in knowledge pays the best interest, right? So we are here to learn, and I hope that everybody will learn a little bit today from today's talk. But you need to think about it every time you go to bed. You need to think about what did you learn today, right? So that's the thing, is that the learning process doesn't stop when you leave university, right? You need to learn every day, everyday life. So now let's start with morphology, right? Morphology of simultaneously propagating hydraulic fractures. That's the topic of my talk today. So let me start by giving you some useful links and on previous presentations and publications on related to this topic, right? So to me personally, it all started back in, I think, about 2016 and 2017, when I talked to Jia Wei Wang from Schlumberger, and he mentioned that what they observe in field scale simulations, that sometimes fractures, when we propagate multiple hydraulic fractures in simulation, sometimes they grow all in parallel, and so they develop nice and regular shapes. And sometimes some fractures grow left, some fractures grow right, and so they develop very irregular shapes. And so that was basically the problem, what was on his mind. But then later on, when I joined Van Gonka Labs, I think in about 2017, 2018, well, that's when I looked at this at a lot of field scale simulations and started making some observations, and it's led to a paper which we published with Roberto Suarez Rivera in 2020 and it's the first paper on this topic, where we analyzed these fracture shapes, as you can see here on the right, as a function of propagation regime, and that's what I'm gonna elaborate more like in this talk. And later on, last year, like in the fall, in summer and fall, so also did several presentations on these topics. Again, here I have like a YouTube link, and then we have like office hours recorded. There's also again, if you prefer to read, then this material which I'm going to cover today, you can find in this in blog post and archive paper. So and finally, I want to take an opportunity to advertise my previous talk at this ARMA hydraulic fraction community lecture series about fracture front tracking algorithm. And again, so this is the simulator or the algorithm which is used right now as part of in ResTrack, and that's the one that I use for all the results which are in this you are going to see in this talk. And finally, if you have any questions at any time, so you can email me. This is my email address, so egor@resfrag.com. I'll be happy to answer all your questions. It's also important to to mention, right, that there are several researchers actually obtained or observed, I should say, this behavior previously, right? So this is on the left, this publication from Mark McClure and his co-workers at ResTrack. This was before I joined ResTrack, and so they published a paper in early 2020 where they discussed that if you propagate multiple hydraulic fractures, as you can see here, four from a horizontal well, if you have a lot of toughness and less viscosity, then each individual fracture is asymmetric and has like a regular shape, more complex shape. But once you start adding up the viscosity or reducing toughness, now you start seeing more regular shapes, right, as you can see here at the bottom, right? So that was observation there. And also, when I wrote the blog post, I received some feedback from Uno and Adam, right, so that they also observed petal fractures or petal-shaped fractures in their simulator, and this is rock field simulator, right? And this is finite element-based simulator, and so it's actually good. It's good news because what it highlights that it's not simulator specific, right? Because here I'm going to show you results which are based on boundary element method, so that no matter what you use, boundary element or finite element, you have similar results. So this is based on physics. It's not based on your particular numerical implementation. So before we jump into fracture geometry, into analysis, let's outline some definitions and some mathematics, if you wish, because we always want to put these results in the perspective. So I want to give you a brief introduction on fracture regimes or limiting behavior. It depends how you want to call it. So if you have any hydraulic fracture, there's a competition between toughness and viscosity, and this competition you can think about it as energy dissipation, right? So the question is whether you dissipate more energy on toughness or on fluid viscosity. Or in other words, you can think about what's the limiting mechanism which precludes quicker fracture growth, right? Is it toughness which precludes longer fracture, or it's a pressure gradient inside the fracture due to high viscosity which precludes quicker fracture growth? The second thing is fluid storage. The question is whether we inject, so when we inject this fluid, whether it stays inside the fracture or it leaks into the formation. And so this limiting case is basically, again, we need to mix and match. So we pick one of the dissipation mechanism, one of the storage mechanism. For instance, if we pick number 2, number 3, so we have large viscosity and small leak off, we have storage viscosity limit, which means that in this limit, the fracture dissipation mechanism is governed by viscosity, which is equivalent to saying that almost no toughness, or the fracture doesn't feel any fracture toughness. And small leak off basically is equivalent to saying there's almost no leak off, right? So likewise, you can say do 1 and 3, and you can say now you have large toughness and storage regime, which means that there is almost no viscosity or no effect of viscosity on fracture propagation. Think about you pump gas or very low viscosity fluid, so you have uniform pressure inside the fracture. That's your toughness regime. And storage means again no leak off. And there are two regimes here on the right, similar viscosity and toughness, but with high leak off. So some equations here. So the thing is that we can outline these fracture regimes for simple fracture geometries. And so today I'm going to talk about the radial fracture geometry and PKN or constant height fracture geometries. So let's start with the radial and see how do we get this definition of regimes and parameters which govern the regimes. So we start with the following mathematical models. Classical mathematical model for radial fracture. We have Carter-Slikov law here implemented, Newtonian fluid, so cubic law for the flow, linear elasticity and linear elastic fracture mechanics here for propagation here at the bottom. And then if you want to do some analysis, so let's do the following. So let's try to estimate the order of magnitude of each of the term. So for instance, so here the derivative of width with respect to time, we remove all these derivatives. So we look at the scale. So it's going to be the characteristic width scale divided by the time scale, and so on, right? So we remove all the integrals or everything, which just estimate order of magnitude or scale of each of the equations. And what happens is that we have 6 equations for unknowns. And you can say, hey, we cannot solve it. And you are right, we cannot solve it. But what it means is that actually there are 2 dimensionless parameters which control the behavior, right? So, or alternatively, what you can do is you can remove two equations, and as soon as you do that, you're going to get a solution, right? It's going to be one of the limited solutions. Okay, so let's do that. So if you want to understand how fracture behaves, say in viscosity storage regime, storage means no leak off, right? So you get rid of leak off. Viscosity domination means no toughness. So you remove toughness equation. Now I have 4 equations for unknowns. And now you immediately, just from scaling, you know how radius depends on time and material parameters. Say here Q is injection rate, E is plane strain modulus, T is injection time, mu is like scale viscosity. And so you get, immediately get just from scaling without solving any equations how things vary with time qualitatively. And then if you do the the more accurate solution, so you'll see that actually these are the scaling multipliers factors, and so that there are so if you want to have a radius, so you get the radius up to this numerical factor, right? So you know what happens if you change the injection rate or modulus or time, how much longer or the radius of fraction becomes. Now you can do the same for the storage again, for viscosity storage. And again, this is toughness storage, supposed to be toughness storage, and so you get, if you do the same exercise, you remove viscosity, and so again you know how your radius and the width and pressure and so on, they vary with time and other material parameters. And again, if you compare it to your classical Snellen solution, uniformly pressurized radial fracture, then I mean you get the right scaling factors, you don't get the numbers. Now why am I doing this? Because the thing is, you want to understand again what parameters affects the transition from toughness to viscosity domination for a radial fracture. In order to do this, we need to equate scaling wise either radii, the widths, or the pressures of the fractures. And so we get this horrible long parameter, but it is what it is. So it's dimensionless time. And so excuse me, so there are a lot of parameters in this time, but when this dimensionless time is relatively small, okay, it means that viscosity dominates. Again, you can look at things like, what if you put zero toughness, right? So how large tau is going to be, and the same large toughness means what if you put very large toughness? But this is dimensionless parameters. It's not just large toughness. So you can have change in modulus or injection rate or viscosity, or toughness or injection time, and so they all affect the result. And here's again a very important conceptual understanding. So I want to understand. So when I talk about the fracture regime, what do I mean? What do we mean by toughness dominates? So the thing is, if you plot for the radial fracture, the radius versus time, I mean your true solution is going to be a black line, right? So in log scale, it's going to transition from one limiting case, shown by this equation, with one slope, and going to gradually transition to another one, right? So it's never going to reach. So you're never going to have 100% toughness domination, right? So it's always going to be like a threshold, right? So what we say, so when this numerical solution within like 1% from this, exact solution of zero viscosity when toughness dominates, that's when we reach this limit, right? But you need to understand this, so it's never precise. I mean, you could put these boundaries, here, or there. It depends on your tolerance, right? So that's important, very important to understand. And so finally, so we're going to finish this introduction on regimes, we'll start on fractures very soon on morphology. So if you put it all together in terms of normalized time and normalized leak-off, because there are two dimensionless parameters in the parametric space, you can outline this map. So where this M zone, the blue zone, this corresponds to parameters where storage viscosity dominates. Again, so it means that we are within 1% of the true solution. If we so for storage viscosity again, it means that we can ignore leak-off, ignore toughness, and we're going to be within 1% of the true solution. And the same is in storage toughness and leak-off regimes. And so that's very important in a parametric map, because with only two dimensionless parameters here, dimensionless leak-off, dimensionless time, we know exactly where we are. So for any parameters, for any modulus, for any toughness, for any leak-off, so for any injection rates, so you can you can compare apples to apples when you do lab test versus field test, or when you have different rock formations and so on. So that's advantage of it. So here's an example how would you use it if you want to scale down the experiment, for instance. So if you take some field values for the modulus, toughness, injection rate, time, and leak-off, and so what you do, you just plug them into dimensionless time and dimensionless leak-off. Again, it's a horrible equation, but you just you can do it even in Excel, right? So, but it gives you like a point here. And so this tells us, for instance, that both viscosity and toughness are important, right? So you are in between. And so in terms of leak-off, again, so these two are leak-off dominated regimes, right? Means you have a lot of leak-off. Here you have no leak-off. If you're in the middle, it means you're probably around, maybe 50% of fluid efficiency, right? Again, you can do it without doing any numerical simulations right away. Now, if you want to increase fluid viscosity, now you suddenly, at this point, now you say, okay, like for 100 centipoise viscosity or 0.1 Pascal seconds, now your toughness is irrelevant, right? So that's the thing. But if you do lab work, and so you have a lab experiment. Now you have the real rock with real toughness, with, field scale toughness, field scale modulus, field scale leak-off. But now you and you use field scale fluid viscosity, right? Like thick water, for instance, here. But you have to scale down the injection rate and time. And you think about you are close to field field parameters, because your fluid is the same, rock is the same, but it's not quite, because you are right here, because you scale down time, you scale down the rate, and so now your mechanism of fracture growth is very different. Now it's toughness controlled and then less viscosity controlled. So that's the things that we can do. And now let's think about the multiple fraction, because that's what we are here. That's the main goal of this presentation, right? Now, so we assume the simplest problem, right? So we have multiple fractures which are all initiating homogeneous formation from horizontal well and under limited entry conditions. So basically, we are saying that the flux distribution to every fracture is uniform, right? So each fracture has the same amount of flux. And homogeneous formation, basically, again, what I want to say is that if you have a single fracture, it's going to be radial. Now we add more fractures, so how radial are they going to be, right? And so the question, what is different from mathematics point of view? So previously I showed you, just a little bit of the analysis for radial fracture, single radial fracture. Now, what do we add if you add multiple fractures? How many parameters do we add? And here is a little sketch for you. So it's horizontal wells, multiple fractures initiating, and so let's look at the parameters which we are adding. Is fracture spacing, how close the fractures are, along the well, the number of fractures, and fracture angle, relative to the well direction. So that, in most cases, fractures are orthogonal, but they could be under an angle. And technically, Poisson's ratio, because what happens for a single radial fracture, all the elastic interactions they're modeled with just a single plane strain modulus, right? But if you look at the Stracharo coefficients for multiple fractures, we have explicit, expressions in terms of Young's modulus and Poisson ratio. They're not like coupled in one parameter. So technically, we need to add one more parameter. But I'm not going to do sensitivity to Poisson's ratio, because typically it's all about the same. Probably I should at some point. But these are the main three. The spacing, number of fractures, and angle. So let's see what happens. And then so let's start simple with, we'll look at closely spaced fractures. And closely spaced means that the characteristic radius or size of the fracture is much larger than spacing, right? So that's like a limit of closely spaced fractures. And that's orthogonal to well. So this angle is, is zero. Again, this is the most common case. And here first, I'm going to show you results from the paper which we published in 2020. And these are using a simulator for Optima. And so again, so this is a parametric space with your domination of viscosity, toughness, and no leak-off here at the bottom, and high leak-off cases at the top. So just put the parameters together, and so if you have, in this case, 10 fractures, hydraulic fractures, closely spaced. And by the way, this is a planar. These are all planar mod 1 fractures, and so on, right? So there's no like mixed mode propagation, anything like that. They're all planar, perfectly planar. And so if you have viscosity domination, then you see they're all pretty much the same. There's some distortion, and again, in ideal world, there's going to be perfectly circles, perfectly radial. And then when you start setting up parameters which correspond to toughness domination, right? So again, you either change the modulus or toughness or injection rate, or I mean, as I said, this is dimensionless parameters, so you can change all of them. So that's what you see. You have real unstable fracture growth, and unstable in the sense, they start off radially, and then very quickly, one fracture goes up, one fracture goes right. And so even though there are 10 fractures here, or 10 initiation points, there are a lot of petals in here, and so they all try to avoid each other. And then obviously, again, we start seeing very, very different morphology here, right away. And then again, for completeness, we do high leak-off cases. And again, it's about the same. If you have a lot of toughness or toughness domination in the system, then this promotes very unstable fracture growth, right? Even though, again, they're mod 1, so it's pure stress shadow which causes leaks. And then once you start adding viscosity in the system, then you start having this kind of pancakes kind of shape, right? They're all the same and equally spaced, right? Equally shaped. This was again our early results, and then with ResFrac again, we want to make sure that this thing is not simulator dependent, right? So that, because I mean, you have different numerical algorithms underneath, you have slightly different implementations. So what if this all just basically, I don't know, one big bug in FracOptima or some other simulator, right? And apparently it's not, right? It's again, so with ResFrac, again, it's very different, not very different, but it's similar physics, right? But the numerical scheme is very different, but the answer is still the same. So I set up 3 sets of parameters. Again, I use different numbers, different fracture size, in this case, different modulus. I mean, I didn't refer to the old paper, but I know where they are in the parametric space. And so if you use toughness domination parameters, again, this is case number 1. So we are here, then that's what we see. So this is an original stretch, just the view, right? So it's not the 2 different simulations. So this is the actual simulation. And then just for the visualization to see each individual fracture, basically we have an ability to visually stretch things along the well by 10 times so that you can see every petal independently. So if toughness dominates, you start seeing these petals like in between. If you this parameter number 2, now you start seeing kind of these weird shapes. And once you are in viscosity domination zone, you still see some instabilities, but they are mostly, there are a lot of overlap between the fractures, right? That's the thing. So here in the toughness domination, there is almost no overlap, only near the wellbore, and then they really avoid each other. And here we have a lot of overlap. So well, that's how things behave. And again, if you want to compare FracOptima to ResFrac, again, different simulators, different authors and codes and so on, and different parameters, frankly, but in the same place in the dimensional space. And again, qualitatively they are the same. And quantitatively, they're different, right? And especially, these ones, each individual fracture is different. And because the question is what controls this instability, right? And by default, these are numerical errors, right? So you have a numerical round of errors, because ideally everything has to be nice and circular, and then at some point you accumulate some numerical error, and now this fracture, shoots left and this fracture shoots right. And so you have different round-offs, and they also depend on implementation, right? So that's why you have different things. And also, when you even run the same simulation twice, you may have slightly different shape for every fraction. And in order to actually avoid this in ResFrac, we add a little bit of perturbation of spatial fracture toughness, like a few percent, so that we have like a determined solution, right? So we don't rely on round of errors to determine our resultant fracture geometry. So now let's look a little bit at the effect of fracture spacing. So now we know that, again, if we have more toughness in the system, we have this, fractures tend to avoid each other, and when we have more viscosity, they try to be like pancakes. And as I outlined in the beginning, fracture spacing is one of the parameters which we add when we add from the transition from a single radial fracture to multiple radial fractures. And so here's the different spacing. So this is in meters. And as you know, in terms of stress shadow, we need to compare the spacing to the characteristic fracture size or radius in this case, because your induced fracture-induced stress decays, as is one of the it's decays in distances comparable with fracture radius, right? So if you're like 2 radii away, I mean your stress shadow is almost 0, right? So there is no interaction. And so, and radius, what is radius in this case? So put here radius in quotation marks. This is, the maximum distance from the wellbore to the furthest fracture. So this is kind of this radius here. But when the fractures are really way apart, then the radius is actually the actual radius of each individual fracture. So it actually changes. So we cannot, properly define this ratio. But we know roughly the range, right? I mean, so it's from 190 to 90. That's where the radius, how the radius changes. But what is interesting is that, again, of course, if you're really far away, that fractures are circular, they don't interact with each other. And if you're in the viscosity regime, I mean, you keep compressing them, you keep bringing them closer and closer, and only when they come really, really close, that's when they start distorting their shape. And in a toughness dominant regime, as soon as you bring them, so again, if your initial radius is not 90 meters, 94. So as soon as the spacing is equal to the radius, now the neighboring fractures already interact. I mean, you might argue that this fracture and you know, say the fifth and the second or the third, they don't interact much, but near neighbors already interact, and so you start having this kind of you know, weird shapes showing up. So that's how it is, right? So and then the next thing is the effect of well angle, right? So it's not uncommon when operators drill their wells, they don't drill in direction perfectly in direction of maximum horizontal stress. There could be many reasons for that, because you have your lease boundaries or previous wells in the region or what have you. And so it's quite common to have a certain angle between the fractures and the well, or so that they don't grow orthogonally or perpendicularly to the well. And so now here I'm plotting your results again. So on the top is toughness domination, in the middle is transition, and bottom is viscosity dominated results for different angles. So 0 means perpendicular to the well, and so 45 means 45 angle to the well. And again, so if we are in a toughness regime, so I should say that practically the results are unaffected. I mean, you can kind of see that you know, because I use the same like a view angle on the fractures. You can see how they are rotating, you know, at different angles. And so now at 45 degrees, you almost kind of look directly at it, but it's just because of this angle. But what's most importantly is that you start seeing the symmetry, you know, like this. I'm trying to schematically show here from top view, so that your very first fracture, you know, goes predominantly left, even in the viscosity dominated regime, and your last fracture grows predominantly right. And the reason for that is because, you know, imagine you have you know, just very small fractures, you know, here and there, right? And your stress shadow acts mostly, you know, perpendicular to the fracture. And so it happens that this fracture, or I should say like this fracture, introduces more stress shadow on this side compared to that side. And so that this fracture, you know, shoots up, you know, asymmetrically to begin with. And so, and then this thing, you know, accumulates with time essentially, right? Because your initial stress shadow interaction is you know, is skewed a little bit. So that's why your fractures are, you know, very asymmetric, just because of the angle, and even if viscosity dominates. And so here's you know, again, a stretched view of this simulation, so that you can see that, you know, clearly that this fracture grows really to the right and this fracture goes really to the left, right? And it's always going to be like this. Even I mean, it's not the fact of that you have a little bit of heterogeneity, right? It's going to be reproducible. It's always going to grow right, and this one is always going to grow left. Okay, just because of the geometry of stress shadow. All right, so we are done with the radial fracture, and then let's move on to constant height fracture. So the thing, and I should have mentioned at the beginning that all this analysis of fracture regimes, right? So in order to do this, we need to have simple geometry, and by simple I mean we need to have a reduced number of parameters, or a smallest possible number of parameters, because once you start adding layers, propant or anything else, you start very quickly adding more and more parameters. Now you cannot do this, you know, simple analysis, but yet you can still learn a lot from it. And so the two fundamental geometries for which we need to do this is radial and constant height, or PKN hydraulic fracture. And because PKN hydraulic fracture, you know, because it's very often, I mean, in field cases, the layers are such that we see nearly impenetrable barriers above and below. So actually, we more often see the PKN type of behavior in field cases rather than the radial. Radial, you know, also happens occasionally if you have like kind of like a mushroomy shape. You know, if you grow into lower stress zone, then the fractures grow upwards, and now you start seeing this more like a radial propagation. But I argue that PKN geometry is also very relevant for field, even probably more relevant for field cases. So let's try to quickly go through you know, again, similar analysis, but for constant height hydraulic fracture, and you're going to see, and let's compare what's going on there. So just a quick review. So for PKN, we assume that fracture height is constant, and the fracture length is you know, much longer than the height, and so that we have predominantly horizontal flux of fluid when we inject here. And this, by the way, is just one wing of a fracture, right? So a single PKN fracture, so it's going to be another wing here. And then each cross section is elliptical for fracture width. And so I'll show you a little bit again, as for the radial fracture, I'll show you a little bit of math and equations for the model so that we are all on the same page. It's okay if you miss anything again, you can I gave you all the reference on the first or second slide. You can go back and read all of this. So if you miss anything, so I'll go fairly quickly through equations. So again, so the governing equations for PKN fracture is we start with a fully planar fracture, and then we say, okay, we assume constant height and elliptical cross-section in all of that, which I said above, and essentially average these equations vertically. So we integrate them over the main layer, so we don't allow them to grow above and below. And so when you average them, now they suddenly become one-dimensional. And what is one important thing here to consider in PKN fracture is the elasticity equation, because technically this is your elasticity equation for planar fracture. If you stick in an elliptical width in here, you're gonna have, you can still integrate analytically here over the vertical average if you want, over the vertical direction, but your kernel here is going to be pretty nasty. So it's going to be, this is kernel G, it's going to be nasty, it's going to have elliptical integral and all these things. But if you look closer at it, even though it looks horrible from mass point of view, it's not that bad. So if you are kind of inside the fracture, far away from the fracture tip, this whole thing becomes like a sine of S, right? So when you differentiate, it becomes like a delta function. And so that's how we go to the classical so-called local elasticity equation, when your local pressure inside the fracture determines the average width or the width in this, right? So it's local, so it's linear relationship between fluid pressure and width, but it doesn't work next to the tip. But if you're next to the tip, now you're behaving instead of sine, you're like 1/s. I mean, because look, this is just nice smooth function. It's almost constant. So if s is small, this goes away, just 1/s here. And so this is the same kernel as for plane strain fracture, right? So you have local, like a plane strain behavior here and local elasticity far away. Now, the reason I'm telling you is again, what's the main purpose? The main purpose is to construct these fracture regimes. We need to know when toughness dominates, when viscosity dominates. If you take classical PKN model, there is no toughness in it, right? It was developed assuming purely viscosity propagation. So we just cannot just do the classical PKN model, because again, if there is no toughness, how can you have toughness domination, right? And so the question is, how do you account for this toughness, right? So that's the whole thing which I'm showing you, is to understand how do we account for toughness, okay? And if you use the full elasticity equation here, right? Then again, if it's like a plane strain here, then you use your classical propagation condition, and which accounts for toughness, just like you use for plane strain fracture, right? But it becomes a little bit more complex for the analysis point of view. And so here's two rivals, if you wish, the way to implement toughness. So one is, again, as I said, if you use this full non-local elasticity and use a standard toughness boundary condition. So from toughness asymptote, right, you say that your width near the fracture tip, it grows a square root of the distance from the tip. You have your toughness modulus here. What are alternatives? And alternatives assume that you have, the first was proposed by Nolte in 1991, is to have some sort of pressure boundary condition. So Nolte said, okay, what if we stick like a radial fracture, uniformly pressurized radial fracture to the fracture tip? What would the pressure be? And so let's use this pressure. And then there was a correction by Sarvaraminin and Garagash later on, quite recently, like 7 years ago. Well, they did a little bit more accurate calculations, but it's still, the concept is the same, right? It's very different by 10% in the numeric multiplier. But anyway, at some point, at my University of Houston days back in 2016, so I compared this PKN fracture with local elasticity and the special boundary conditions with full solution, and they are not bad, because the comparison is not bad. So here we see the full comparison. Again, we have this near tip behavior for the weights and so on. And then for this local elasticity solution, you have discontinuity at the tip, you don't capture the tip, but the overall widths and lengths are okay. Even actually for both models, but this is a little bit more accurate. So my point here is that if you want to solve something numerically, then go with non-local elasticity. For the analysis, I'm going to proceed with local elasticity analysis, even though I know I'm adding a little bit of discrepancy near the fracture tip, because it's just fewer number of parameters, easier to analyze, and so on. And I think this is the last slide with equations, so bear with me, and then we start going with I know, with pictures and results. So the point of this slide is to show that, again, if you do similar dimensions analysis as we did for the radial fracture, if we start, we can normalize and reduce number of unknowns here, and there are two dimensionless parameters which determine parametric space. It's dimensionless time and dimensionless leak-off, but the expressions are very, very different. Now we have fracture height involved here, and and the combination of parameters is different. But the thing is, we can do this analysis and we can construct this parametric space. And again, if you are curious to see how it's done, I mean, here's the reference for you. You can go and look it up. But the idea is the same as for the radial fracture. So we have the parameters for our PKN fracture: injection rate, leak-off, toughness, modulus, viscosity. You put them in, you have dimensionless time, dimensionless leak-off. It gives you a point here in parametric space. Now, if you are here, it means toughness dominates, right? It means you have relatively large toughness. If you are here in M regime or blue regime, it means that viscosity dominates, means you have relatively high effective viscosity. And again, and this dimensions parameter is very, very different from the radial fracture, because at least now, because we have fracture height. And but again, this gives us an ability to compare apples to apples, or have some reference point if you do simulation for multiple fractures, because now we know where we are. And sure enough, so again, so I set a few parameters, so set a few runs. And actually, this time I didn't do leak-off, because leak-off was we didn't see anything interesting, if you say, when we add leak-off. So it's about the same. It's all about toughness to viscosity transition. So 3 runs: one corresponds to toughness domination, one viscosity domination, one in the middle. For PKN type geometries, we have constant heights. I put a lot of barriers, very strong barriers above and below. I wanted to make sure that fracture length is much longer than the height. In this case, it was like about 5 or maybe 7. And that's how results look like. Again, it's original spacing, right? So this is all the dimensions are true to size, and stretch 10x, which are stretched 10 times along the wellbore, so that we can see each individual fracture. Okay, and again, so we see a lot of fracture interactions, the shadow interaction between the fractures if toughness dominates, right? So each individual fracture doesn't even reach the whole reservoir height in here. So there's a lot of interaction. Some fractures go left, some fractures go right. Once you add viscosity, now situation is very different, right? So now we have all nice and equal hydraulic fractures. Well, they are shorter, right? Because you have, if you have everything the same, because you add viscosity, you add more resistance, but they're all the similar geometry. Well, near the fracture tip, there are some distortions, and we also saw some distortions for radial fracture. So, but again, globally, they are the same. And again, and for PKN type fractures, this is just a slide showing that the stress shadow reduces as a function of distance over the fracture height. Just not the fracture radius, it's fracture height. And so when we do analysis with respect to spacing, we can do spacing over height ratio. Previously, it was spacing over radius, but for the radius, we don't know exactly the radius, but height is pretty much determined in here. So we have a little bit more kind of rigorous dimensionless parameter here on the x-axis. And again, if you have viscosity dominations, fractures far apart, and then you start bringing them closer together, there's almost no interaction. It's just a little bit near the fracture tip. And when you have toughness domination, you have such parameters that relative toughness is really high. Then again, even when 1-to-1, so when your spacing is equal to fracture height, they already start interacting. Some fractures go left, some fractures go right. And so you bring them closer, and now you start having this weird shape. And this is, by the way, if you try to run these things multiple times, or if you try to even add even more toughness, this is still the same. Or one reviewer asks for mesh dependence to see if you change the mesh, things are going to be the same. And again, they are qualitatively the same. Again, each individual fracture is a little bit different, but they qualitatively they're very much the same. So the fractures really avoid each other, and when toughness dominates. And then the effect of angle. Again, this is a well angle, and as you can see how we are kind of rotating this view from left to right here, and again we start seeing this very similar asymmetry as we saw for the radial fracture. One difference here that even for the toughness domination, for toughness domination, these fractures grow full reservoir height in here, so they become very asymmetric. But again, they grow full reservoir height when you start rotating them. So they start having more regular geometry, if you wish. And here's just a stretch like this case, so that you can see again. So these fractures goes right, and then it's in the middle, and then again left and left. Right, so that's the effect of the angle, right? So you're always going to have this fracture asymmetry if you start having the angle. So fracture regime is not going to work. It's not going to help much, for the viscosity domination. So you're going to see it just for less to a lesser extent. And then quickly for the field case, again you can. It's hard to argue that this is actually the constant height hydraulic fracture, I admit, but you can still do some estimates. And so based on the estimate, this is more to toughness domination, this is more to viscosity domination, and there is an angle between fractures in the well, so you can see the fractures go left here and right there. But the difference that here, they also like segregate on vertical, right? So there's some, lack of overlap vertical direction. Here they, all grow, up, all the way to the reservoir height, if you wish. But there are other examples, and actually there were interesting things. So we recently compiled the data for several field cases, and guess where all the data comes from the parametric space? It is all over. So there are cases which are following the viscosity domination, cases go into toughness domination, things in transition. They're all over. So let's try to look at this parameter again and understand why is this the case. And I think it's real. So this is a parameter dimensionless time that determines where we are, right? So if it's less than roughly 0.1, toughness dominates. Roughly less than 10 to the 3, then viscosity dominates. So we have Young's modulus here, E, or plane strain modulus. We have viscosity, injection rate Q, injection time, fracture height, and toughness, right? And there are very different powers of this, but in general, if you have stiffer rock, so you increase Young's modulus, high viscosity, higher rate, longer injection, then you have more viscosity domination, right? So you increase tau, so you go, it becomes larger. If you increase fracture height or toughness, then more toughness domination. But the thing is, it's the fracture height which also a parameter, and it's something which you don't really control, right? So you may have the same rock with the same injection, and you just go from one formation to another. I mean, it's not identically the same rock, but roughly the same toughness, scale wise, roughly the same Young's modulus. But you change the fracture height by a factor of 2. Now you see this, it's power 3.5 in height. Now you're off, right? Now instead of having viscosity domination, you can be in transition, for instance, or you can change toughness even a little bit because it's huge power of toughness. Now you jump off the transition. And interesting enough, the viscosity has only the first power. So really, I mean, with all things being equal, you just switch from sleek water to linear gel. I mean, you don't change things much. And the modulus, typically we don't think about the modulus being very important, but it's power of 4, and it's quite often that we can see formation which different. I mean, you can go have 3 million psi modulus, and then you can have 6, 7, 8 million psi modulus. I mean, change by factor of 2 to 3 to the power of 4, it's a big jump. So that's why we have things all over. So there is no unique solution like, hey, we have shale, sleek water, we gotta be there, right? It's not like that. And again, in general, we also often see that skinny fractures, like small height, are more likely to be viscosity dominated, so they don't interact. So it's when you start growing in height that's when you start seeing, things, complex morphology to happen. And the last slide is one, just give you like a little hints or just food for thought in terms of how can it be used. And right now, it's very common to use fiber optic sensing and in offset well to detect frac hits. So basically, you put an observation well here, you put a fiber in here, and then you see the fractures approaching here. And this fracture approach, you start seeing this, this ears from your stretch shadow. You stretch in the cable, and then you start seeing the frac hits. But excuse me. But my point here is that not all fractures arrive at the same time, right? And so. And it probably means that we are not in the viscosity dominant regime, because otherwise all fractures would arrive at the same time. Again, all things being equal, I mean, because there are other things happening here. You have like non-uniform erosion between the clusters. You have non-uniform property distribution. But again, assuming that all things are being equal in this case, so we are not in the viscosity dominant regime. But maybe we're in toughness. Well, maybe not, because if we're in a toughness regime, that we would see only one frag hit from one because they all avoid each other. And so, but again, this is radial, but maybe we have constant height. But the thing is that we can, in fraction morphology, is something that we have some indirect observation from this, from field data, and something that we can use to history match the field data. So that's something to keep in mind. And now, as we know these dimensionless parameters which control the morphology, we know what to change in order to better represent field data. So finally, here's my summary. I think we are on time here. So I want to remind you, so there are four, in terms of the analysis, and again, we always want to put things, even for multiple fractures, no matter how complex the problem is, we always want to, scale it down to the simplest problem we can still analyze, because we can learn a lot from simple problems. And so for the simple problem, for simple fracture geometry, such as radial or even plane strain, we didn't talk much about it, but in PKN, there are four limiting solutions, right? The four limits for single fracture, which are storage viscosity, storage toughness, leak of viscosity, and leak of toughness. And for each of these geometry, we have a parametric space with two dimensionless parameters, which determine where we are. And if you're only concerned in terms of transition from viscosity to toughness, it's only a single parameter. It's only one parameter, but it's unique for each geometry. And one dimensional parameter which has viscosity, toughness, modulus, injection rate, all of these combined, which determines where we are in terms of the physics that dominates the response. And for the multiple fractures, and again, it's very important with limited entry. Limited entry means that each fracture has equal share of injection rate from the well. When we have viscosity domination, no matter what the geometry is, as soon as viscosity dominates, we have more or less uniform fractures, identical to each other. And when toughness dominates, now we start seeing complex morphology, right? And finally, again, this mathematical analysis for this stability for this problem is still not done. So if you're brave enough, so it's a great opportunity for you to do it. I'll go and support it with both hands. And finally, the last thing, again, if you miss anything or you prefer things to be, you prefer reading, right? So this is a blog post, all of this runs, all input there is all in there, so you can go ahead and read it. So thank you all for your attention. Now I'm ready to answer all your questions.
Thank you, Egor. I mean, this is outstanding work, and you have generated some questions. Let's just see. You has asked. He wants to understand the effect that a higher fracture toughness tends to have, and in creating more complex fracture networks. I mean, does it mean that a higher fracture toughness can be correlated with a brittleness index, which favors fracture complexity, or do you have some philosophical comments about that in general?
Okay, well, so we need to understand, there are some differences, okay? Here I'm talking about the model, okay? And the question is, what is the brittleness index? And there are, I saw like, 5 different definitions of brittleness index, right? So the question is, what is, it depends how you define, how you correlate it, most importantly to fracture toughness, right? And to your stiffness. Because in this model, again, what we assume linear elastic fracture mechanics. So the rock is quantified by fracture toughness, and it's linear elastic, so it's Young's modulus Poisson ratio. So these are the main parameters. And so the question is, how do they correlate to this brittleness index in for given definition of brittleness index, right? And so that's how we can do conclusions. Because for me, again, I speak in terms of toughness and modulus. So again, you take a brittleness index, correlate to toughness modulus, and then you go to these dimensionless parameters, and then you can see if it's high or low. And then, you go between the viscosity, toughness, domination. Now, the second thing is about this SRV and fracture complexity. Again, there are no natural fractures, and here the fractures are assumed to be planar. And actually, by the way, a lot of these fiber optics observations and confirm the fractures are predominantly planar. And so, but the SRV, I mean, that's a very good question. At some point, we did a study and try to see what happens if you have everything equal, but you just change the viscosity. So if your rock is the same, injection rate is the same, toughness is the same, we change the viscosity, because it looks like you have more fracture surface area when viscosity dominates, right? Because it looks like they're, see, I mean, here you're losing fracture area because the fractures do not overlap. Here you have a lot of surface area, more contact to the reservoir, and intuitively it looks like that this is a better solution. But when we plotted the surface area versus viscosity, it goes up a little bit when in an intermediate regime between viscosity and toughness, and then it goes down. So when viscosity dominates, actually it generates less surface area. Why? Because fractures become much shorter, right? Become much shorter. And again, here it's just all the visual, right? I mean, I set up the parameters such that they are all roughly the same size, but if you change just the viscosity, your fractures become shorter and wider. And so actually, when you into the viscosity domination, you start losing your SRV or you're losing your total surface area in contact with the reservoir because you make the fracture shorter. So that's very important thing to keep in mind. Okay, so I hope I answered your question.
You have another question from Ali Donashi, and Ali appreciates the mathematical derivations, but he would like to just comment a little more on what the practical use of the analyses are.
Right,
how
right.
Would one take full advantage?
Absolutely valid question. I mean, the first thing is, I mean, this is to understand what is going on, right? I mean, there are a lot of questions. There are a lot of people observed. I mean, as I mentioned in the beginning, I observed this petal-like behavior, but now with this analysis, we understand why. Okay, we understand why, and we understand what parameters control this. Okay, so we understand what can we change in the design potentially to achieve toughness or viscosity domination. But as I said at the end, right, probably this question was before the presentation. I think one of the biggest thing is to try to calibrate the field data, because if you have fiber optics data, you know, your frag hits, your frequency of frag hits, or some statistics of frag hits. So when they come at what time and how uniform the different fractures hit this well. Well, that's this data. If we calibrate to this data, well, that's when we can use this analysis to guide us to basically to change the certain parameters, like toughness or viscosity, whatever we use for the history matching, so that we match the field data. So I think that's what I see. And again, and if anybody else sees anything else, well, I mean, you're welcome to shout out. And also, again, it's for scaling between lab and the field, right? So if somebody will ever want to reproduce such thing, such weird, such confirms such weird, petal shapes in the lab, right? So we really have to do this analysis so that we scale down properly from field to lab, right? So that's another use of this, well, as he said, fancy math.
Let me ask a question. Write the slide that you have here. If if I'm fracturing a granite, I'm assuming the toughness you're talking about is the same toughness that we measure in the laboratory. If I am fracturing a granite with water, are you saying that you're going to get fracture shape like the petals on a flower that you are showing on the right-hand side of your slide? Is that what you're implying? Right.
Well, okay. So if you fracture granite, right? So, well, it actually depends because we need to put the numbers in, because I'm not sure exactly what the modulus is, because if you have really granite is probably pretty stiff. If you have a lot of modulus in there, you still can be in viscosity domination or in transition, right?
So I'm fracturing this. I'm fracturing a granite with water. So the water is the low viscosity fluid, and granite has got very high toughness. Are you saying that if I fracture like that, I'm going to get the picture that you're showing on the right-hand side of your slide, like petals on a flower? Is that what you're saying? The fracture would look like, multiple fractures will look like that? Is that
Oh.
the answer? Is that correct or wrong?
Well, if all conditions are met, then yes. But I mean, by all conditions, I mean you need to have planar fractures, right? Because I assume that fractures are planar and purely mod 1, right? So there is no local heterogeneities and so on, right? So it means certain state of stress, right? And I assume you are limited entry, right? And it's very strong assumption, right? Again, it happens in the field, but again, if you want to go to lab, for instance, it's really hard to realize. It's why, I mean, all experiments in granite, like in the lab, they never look like this, right? Because again, all the assumptions are not there. But if you satisfy all the assumptions, yes, I'm saying that's how the fracture should look like, at least according to the model. And again, and you can argue about the model, but it's different fracture simulators show the same thing, right? And
look, the question of model is the mathematical entity.
correct.
The question is the practical application of this. And what my personal view is that the fracture that you're showing on the right-hand side, like petals on a flower, that kind of a fracture in reality can never exist.
Well, I mean, this is an argument, right? I mean, the thing is that we do not know, right? I mean, we do not know. And I guess, I mean, the best thing to settle it down, right, is to do lab experiments, right? And I think if somebody will ever do in a good lab experiments and trying to reproduce this, that's probably going to be the best way to prove it. I mean, look, this is a model, right? But again, what you are saying is an argument. I mean, you say it cannot exist, but we don't have a strong confirmation, right? That this never exists, right? So,
Egor, Ali, if I can jump in, Roman Bilak with Terralog, let me comment. We have fractured granite type rocks extensively in China, and really the short answer is with water. If you do it cyclically and there's a little bit of proppant loading and you manage that strategically, I don't know about petals, but Egor is quite correct. The data analysis we've done, pressure fall off, stress analysis, et cetera, does show complexity developing in the fractures. So in granites or granite type rocks with water, very light proppant loading, cyclic injection, you do get complex morphology. Again, I can't speak to petals and things, but data does show in that toughness dominated regime, complexity does develop, if that helps.
I don't argue with complexity. I'm talking about particular shape. Yeah.
Yeah, petals I can't speak to, but in terms of complex morphology, it definitely happens.
and again, I mean, going back to petals, I mean, this assumes that we have no layers, no other heterogeneity, right? So, I mean, this is ideal case of radial fracture. And of course, in field scale simulations, we don't see these nice petals. As I said, if you could go back on the slide up and down. So we see something like this. I mean, but one fracture is above, one fracture is below, right? So it's kind of like petals, but not, this is a very idealized case with no layers, and we always have layers. And so again, and if you look at the constant height fractures, again, it's like right here, right? It's more like some fractures go left, some fractures go right, rather than we have petals. So again, don't get just jump on this particular shape, because again, it's very idealized conditions, right? And it's really hard to reproduce them in the field. But the thing is whether we see more complexity when toughness dominates and less complexity and more regular shapes when viscosity dominates. That's kind of the main the main observation here. Sorry. All right, so I hope I answered your question. So again, but we can chat later on if you want to.
Well, and I'm not sure we're going to get through all of the questions that are generated here today. So what I might recommend is that everybody has Egor's email, that you should communicate directly with him. Egor, would that be okay?
It'd be okay, but I mean, I don't mind to stay for another 15 minutes if everybody is okay. I mean, I can answer some of them and try to be quick.
Okay. So where did we end up? Jeho Wang enjoyed the presentation, and he's wondering about examples from the Permian or other basins that we might be familiar with.
as I said before, I mean, for constant height fractures, we are all over because you change your modulus, you change your, again, depends how you do history match. If you change toughness, you can really be all over the place. So there is no unique thing. For radial fracture, it's a little bit easier because you don't have additional parameter of fracture height. And as I recall, for radial fracture, we are roughly in the middle between viscosity and toughness domination for most of unconventional plays. But for constant height, we are all over.
Okay. And then let's see. Yue Guao is interested. What on your axis? What does tau mean on the y-axis of? Let's see. On the slides of spacing of multiple hydraulic fractures.
Okay. Yeah. So sorry, I didn't answer this. So this is the log of tau, log 10 of dimensionless time. So basically, if you go back to parametric space, so see this axis, so it's log 10 of dimensionless time, so that if it's about -1, then it's where toughness dominates. It's about like what 1 to 2, that's in the middle, and about 4 that viscosity dominates. So basically, I take this axis, this log of tau, and I plotted it here, and so that if it's about 4, then viscosity dominates, right? So if you go back, it's about 4, so we have viscosity domination. It's about -1. That's where toughness domination, right? And so that's the y-axis. So this again single parameter which determines the which mechanism dominates.
Okay, cool. And Suresh Dadi, he was wondering about microseismicity, and I think that you've showed an example that answered his question there. That indeed it has relevance. And Newer is interested in the selection of your time, whether it's simulation time or real time.
Simulation time or real time. Oh, this is no, this is pumping time, right? So you pump, I don't know, 80 barrels a minute for 70 minutes, right? So that's the time that you put in, right? So for how long? And this, by the way, all the runs assumes constant injection rates. So if you put your 70 barrels a minute, for 1 hour, so that's what you put 1 hour for your time. Okay. And
Professor Wu, let's see, enjoyed the presentation, and for multiple fracture cases, you comment on the fluid distribution. Yeah, what about the fluid distribution in each cluster? I think you've answered that, but maybe okay. Subsequently to this question.
Okay, so yes, so the fluid distribution is assumed to be uniform. So basically, so what it is a put relatively high perforation friction, and then I checked after the fact that the fluid is more or less like to within few percent is uniform. And again, you can play with non-uniform, and I did it at some point, but again, it's an additional parameter. And once you start having more and more parameters, then it's really easy to get lost in all this parameter space. But we can do that as well. And then the second question was about shear displacement discontinuity. How does it affect fracture morphology? This question was also asked before, and it was like a more broad question. What if you let fractures turn? How it will affect morphology? And the answer is it doesn't affect much. Previously in Fracoptima, because when I did it for the paper, so one of the reviewers asked to simulate these curved fractures, and I did, and it looks pretty much the same. Maybe just a little bit of variation. And I try to simulate with shear discontinuity and without, and it's all about the same. So it's mostly the normal normal stress which affects this behavior.
And then I'm moving down to Dimitri's question. How noticeably will the reservoir simulate? Will there be a change if you replace symmetric bi-wing fractures with your complex fracture geometry?
Right. So the thing is, well, of course, I mean, right. I mean, when you do a real, project, right? I mean, everything is important, right? So because once you fractures start grow weirdly, now your proton distribution can become really weird, and so it will affect production, connection to the reservoir, and so on. So things change. I mean, I cannot give you the numbers, how much things change, but I think it's I mean, you change fracture geometry, I mean, you do change production, definitely, right? That's for sure. The second question, whether the fracture complexity is absolutely necessary for the industry. Well, it depends what you call fracture complexity, because typical when people say fracture complexity, that they talk about fracture, natural fractures and things like this. But here's a different fracture complexity. Here is even if you have planar fractures, just because of stress shadow and limited entry, we start seeing this different morphology. And the question is, it's not about like necessary or not necessary. The question is whether it is there or not there, right? I mean, if it is there and we have enough evidence to confirm that it exists, then it is necessary. But if we, now we know the theory that it's possibly there, but now, well, let's start to do field evidence, right? And so if field evidence will suggest it's not there, I mean, I'll be fine with that, right? But if it's there, it is there, right? So then it is necessary. So that's my opinion on it.
And so the next question goes back to, it's from Roman Priol, and it just goes back to the discussion with Dr. Donaghy, about pedal versus radial shape and what the role of heterogeneities are. And I don't know whether you want to comment on that further.
Right. So I think this is a very valid question, right? So basically, what the question is saying that how predictive can it be in terms of geometry, right? Even if you have this radial fractional layers, so what I said, I mean, if you say do numerical simulation twice, then you start seeing different, slightly different geometries of each individual fractures. And so that if you add a little bit of heterogeneity, which we always have in the field, now it's going to be more predictive and more stable. But again, we don't know this level of heterogeneity. But it's very important to understand that its geometry of each individual fracture is very different. But the overall geometry, if you look at it as the whole stage, right? For instance, if you look at this, the outer radius of the whole system of fractures, right? It's always the same. Or pretty much the same, so that the overall geometry, if you kind of like combine all these fractures, especially when it's the same, but each individual fracture is going to be slightly different. So well, we can do statistical realizations, but again, the overall results for the whole stage are pretty much determined, right? So that's good news. At least that's what I saw in different simulations.
So I'd like to end with one final comment from the audience. It's from Shendong Chang, and he says he was glad to join this talk. It's 1 a.m. in South Korea, and Egor, it makes him happy to stay up and listen, and he thanks you very much.
Right. Thank you all for your comments and for your questions. So
yeah,
right. So
very much appreciated.
Egor, do you have a minute after I want to talk to you? I think I have some possible explanation for some of the stuff you're seeing. I could talk on offline.
Yeah, absolutely. Let's chat. Absolutely, I'm available.
Thanks, Egor. Great talk.
Thank you, Anthony.
Thank you very much. Fantastic talk, Egor.
All right, thanks, Romain. Thank you, everyone. So it's
all the best. Thanks.